Welcome to another installment of Concrete Mathematics. Today we're going to have Professor Norman continue his talk on ADE graphs with a lecture called ADE graphs, lattices, weights, and quarks.
Thanks, Sebastian. So welcome everyone. Today I'm going to continue on this journey to try to understand some of the fascinating mathematics around the ADE graphs from a kind of graph theoretical point of view, thinking of the graphs as primary and trying to build up a structure from them. And today I want to touch base on some other things. I want to talk a little bit about fabulous lattices and some interesting classical problems. Then I want to touch base with weights, representation theory or Lie algebra. There's this sort of duality between roots and weights. So I want to introduce that in this elementary fashion here in the context of graphs. And then eventually I want to talk about the numbers game, which is a dual game to the mutation game. That will sort of allow us to see things from two different points of view. And then I'll talk a little bit about some applications to the standard model in modern physics. So I'll only give you a rough overview of things there, and probably most of what I say is not entirely correct, but at least we'll connect a little bit with some modern physics. Okay, so we're going to start with the idea of a lattice. So a lattice, simplest lattice is this one in the plane, just integral coordinates. And there's another famous lattice in the plane that you get by looking at lines which are 60 degrees spaced like this. And that's the sort of hexagonal pattern. And that's famous because that's the most efficient way of packing circles in the plane. If you want to pack circles, you can do it by putting the circles at the centers at these nodes. And that's the most efficient way of packing circles in the plane, as Gauss established some close to 200 years ago. Now, an interesting natural question then is to extend that to higher dimensions, and it's a classical question about, say, the best density or the greatest density in space for packing spheres. Well, grossers all know how to do this. So what you do is you just get tennis balls, let's say these are our spheres, and you lay them out on the plane in a hexagonal fashion like this, and then you put other tennis balls on top of the existing ones in a repeating pattern. And there's actually a couple of ways of extending that. Actually, there's a lot of ways of extending that to a three-dimensional story. But the most common one is when we do it in this kind of a regular fashion. So if you have 6 balls like that, then we're going to put, say, around the central one, we're going to put 3 others. Well, we could put some kind of holes here, so we could sort of put them here, like in that kind of configuration. Or you could put them in the other configuration, where you're using the other 3 holes. And so if you consider one of those to be of type A and the other of type B, then what you can do is as you go up up the levels, you can sort of alternate with the original one. Let's say the original one was type A, and then this red one is type B. And then the other one, maybe a green one, which will be overlap sort of like this, that would be, say, type C. Then you get the so-called face-centered cubic lattice, or FCC, chemists use, by alternating A, B, C, A, B, C, etc. And then this is the lattice that we can think of visualized this way here. So there is sort of hexagonal lattice that we've seen in 2 dimensions, and then if we put that horizontally, then we can stack ones on top of this, and then we just sort of use this as a lattice, think in terms of vectors emanating from a fixed point and just taking integral combinations of fixed points, and we get the face-centered cubic. So these are all examples of lattices. So what is a lattice? So a lattice in n dimensions And I probably should say that for us, the n-dimensional space will be over the rationals. Turns out to be rather important from my point of view, but also actually for this discussion of lattices. It's better to think about having vector spaces over the rationals. So a lattice in dimension, n dimensions, what is that? It's the integral span of a, well, actually a basis, but actually just a spanning set. And in the 19th century, Hermite made investigations like this and basically did kind of row reduction on integral fashion, and was able to sort of find canonical forms for lattices and so on. So that the even if you start with a spanning set, which is much bigger than the dimension, if you take all the integral combinations, you're still going to get something which ultimately can be written as an integral combination of n vectors. So let me give you an example. Over here we have well, a lattice. So over here we see here's the center, and maybe these are the integer points, like 1, 2, 1, 2 in the usual xy plane. And the black points form the standard integral lattice. And with basis vectors, say this vector here and this vector here, so integral combinations of that will span the original lattice. And then if we go along and add another vector, let's say this one here, so now we then extend our pattern, all integral combinations of all those three vectors, then you get the picture that you see there. That still ends up being a two-dimensional lattice and says that you can find a basis for it. In fact, this basis vector and this basis vector will span the lattice. It's just integral combinations of those two vectors. Okay, so a natural question is, what are the best lattices in 3 dimensions or in higher dimensions for packing spheres? And Kepler suggested that the FCC lattice gives the best packing in 3D, irrespective of whether it's a lattice packing or not. So you don't have to pack according to the centers being on a lattice. You could just pack in some kind of random fashion. And so that gives you more possibilities. But the conjecture was that, in fact, the lattice packing, the face-centered cubic, is the best packing. And that was a very famous conjecture, which was open for a long time, and only successfully solved by Thomas Hales around 20 years ago. So established that actually was true. So what about in higher dimensions? Well, the Bible in this work is volume by Conway and Sloan, and there you get all kinds of information, but here are the best packings. So here's the dimension, and here's the best packing lattices. Okay, so 1, 2, 3, 4, 5, 6, 7, 8, and the best lattice packings are Z, and then A2, A3, D4, D5, E6, E7, and E8. So it turns out that the best lattices are the ones obtained from Dynkin diagrams. These are Dynkin diagrams that we've been talking about in our lectures so far, and up to 8. That's sort of where a nice list ends. And then after that, things get a little bit trickier. And in fact, the best, other than 8, I think the only one that we really know about is in 24, where there's an even more remarkable object called the Leech lattice, which is some kind of big sort of extension of all this ADE business, or it's some kind of thing that goes beyond the ADE story, which is quite interesting, and actually also connected with E8. But for other dimensions, it's not really known, I think, what the best packing lattices are. So I will explain what these lattices are in a second. But I want to also just describe a second problem, a related problem, which is the kissing problem. So the kissing problem is, also goes back to classical origins. If you have a sphere, you can ask, how many other spheres can you put adjacent to the given sphere? And one way of solving that is to take the icosahedron. Here's the icosahedron, and there's a central sphere, and there's 12 around it. And if you imagine gradually blowing up the sizes of these spheres, at some point, the 12 outside ones will all touch the inside one, and so then you'll have 12 outside spheres touching the central sphere. And so it's a question, though, if you actually look carefully at the geometry, you'll see that these red bonds are just a little bit shorter than the blue bonds. And that means that when you actually get to that stage, there will be a little bit of space between the spheres that are around the central sphere. None of them will be touching each other. And there's space then to wiggle them around. And maybe there's space to sort of move and put them in some position so that a 13th one will fit in. And this is the source of a great interesting controversy between actually Newton and David Gregory. Newton said that 12 was the best you could do. And Gregory thought maybe you could put in a 13th one. Well, as usual, Newton was right. But that was not actually solved, I think, for another century or so afterwards. So now there's a corresponding problem in higher dimensions. If you're going to restrict your spheres to be centered around lattice points, what is the maximum number of spheres that you can get touching a given sphere? What lattice packings will give you the largest kissing numbers? And so largest kissing numbers. And here the answers are Z, A2, A3, D4, D5, E6, E7, and E8. And the kissing numbers are, so the number of things spheres that you can put around the central one, for 8, 2 in dimension 1, and then 6 in dimension 2, that's that story there, 12 in dimension 3, and then 24 for D4, and then 40, and then 72, and then 126, and then 240. And these are just numbers involved in the root systems that we've talked about in previous lectures. So these are the numbers in the root systems. In other words, you just take those vectors, they're all sort of close to the central one, and they are all touching the central one. So the ADE graphs provide us with pleasant answers to these classical problems. And also, again, beyond 8, somehow there's a boundary there, and I think not so much is exactly known, although lots of estimates are known and so on. But in terms of exactness, I'm not sure what's known beyond that. So let me tell you about the lattices. So what are these lattices actually? So independent of playing mutation games, so you can just define the lattices. So AN actually turns out to be in n plus 1 dimensions describable most easily. So in n plus 1 dimensions, you look at vectors x1 through xn plus 1, and they're all integer. So I'll write integer to the n plus 1. With the condition that the sum of the xi's is 0. That's the AN lattice in any dimension. And the DN lattice is also in any dimension. So now we're in n dimensions, so x1 to xn in integer to the n. And this is given by the sum of the xi's are even. So before I tell you what E6 and E7 and E8 are, so let's talk about these ones. So there's the face-centered cubic is the same as A3, and that's also really the same as D3. We haven't talked about D3 as a separate Dinkin diagram, but you might like to think about D3 as being this one. It just doesn't have anything to the right. So it's really the same as A3, but somehow from this point of view it's slightly different. So there's actually two different ways of thinking about the A3 of the face-centered cubic lattice. One is to think of it in terms of span of the four basis vectors in four-dimensional space. Okay. But in three-dimensional space, if you want to cook up the face-centered cubic, you can do it this way. And this is makes it a little bit challenging sometimes to understand this lattice, because even though this version of it is rather simple, stacking balls, the actual representation as a lattice in this model is a little bit different. So here is the standard integral lattice, 0, 0, let's say, and maybe I should put it in a certain way. It doesn't matter really, but okay, let me put it this way. I'm more comfortable with that. Okay, so here's 0, 0, and here's the standard basis vectors, x, y, z axis, 1 in every direction. So that's 1, 0, 0, okay? So these things here that you see are the integral points. Now, from this point of view, the dn lattice is the set of all points. They're integral, so they're a subset of the white balls, but it's a subset such that the sum of the coefficients is even. So in particular, 1, 0 is not in there. 1, 0, 0 is not in there, but 2, 0, 0 is. So the elements in this cube are 0, 0, 0, 2, 0, 0 in there, but also the centers of the faces, like this one is 1, 1, 0. That's why it's called a face-centered cubic. That's why the chemists call it that. And to see the regular face-centered cubic, you have to tilt this one. I don't know if you can see it here, but I've put inside this thing this green plane, and can you see that green plane sort of there? There's one there, and there's another one over there. So that if you look just at those 2 points and this one here, there's a green triangle there, which is exactly the same as this green triangle. So if I sort of line them up the right way, you might see the correspondence. Okay. So I'm kind of putting them in parallel here. Okay. So you have to, if you're looking at the standard lattice like this, you have to think of the face-centered cubic sort of slanted in there like this to make the correspondence. Okay, so that's AN and DN, and then what about E6, E7, E8? Well, it's easiest to actually describe E8, which is a completely fabulous mathematical object, the lattice E8. So it turns out that it's the first even unimodular lattice, which is some technical thing. Unimodular means that it's actually equal to its dual. So if you have any lattice and you look at the vectors which are whose dot product is always integral with respect to the lattice, you get another lattice called the dual lattice. And E8 is a unique lattice less than dimension less than or equal to 8, which is both even and unimodular. And how do we get it? Well, we get it by taking D4 plus D8 plus another copy of D8. Let's call it D8 tilde. So to explain that, so here is the unit cube in 8 dimensions. Okay, so this is 0, 0, 0, 8. There's 8 of these everywhere. Here's 1, 0, 0, 0, and so on. Here is 1, 1, 0, 0, 8 of them altogether. Okay, that's the unit cube in 8 dimensions. Now, if we look at just D8 by itself, we're talking about the points whose sum of the coordinates is even. So that includes this point here, and it includes this point here, and it includes that point there, and so on. Now, if we think about the center of this unit cube, the center of the unit cube is the point 1/2, 1/2, all the way up to 1/2. In our regular three-dimensional space, if you take the unit cube, which is one of these little ones, and you look at the center, and you look at the distance from the origin to that center, or actually better, the quadrants from the origin to the center. Quadrants is sum of squares of coefficients. Sum of squares of differences of coefficients. Then that quadrant is going to be less than that diagonal across the face quadrants. The sum of squares here is 1 squared plus 1 squared, that's 2. But here it's something smaller. But exactly in 8 dimensions, the quadrants between these two things is also 2, because the sum of the squares here is 1/4 plus 1/4 all the way up to 1/4. There's 8 of them, and that sums to 2. So that quadrant there is equal to this face quadrants of 2. And that means that you can stick a sphere right in the middle of this unit cube, which has the same size as the sphere that you've got around these 2 points, which are supposed to be touching. There's room inside the unit cube for another such sphere, exactly the same size. And that means that you can take the entire D8 lattice and translate it by exactly this vector. And then there's just enough room in 8-dimensional space for this second copy of the D8 lattice to sit and interact with the one you've already got. So that's the E8 lattice. And then the E7 lattice, basically what you do is you just take a unit, the smallest vector, and you take the orthogonal complement, and then to get E6, you take an orthogonal complement of a 2-dimensional configuration. So the E7 and the E6 lattices are sort of derivatives of the E8 lattice. Okay, so now I want to talk about, ultimately there'll be 2 interesting lattices coming up, but we have to go back to our graph theoretical point of view now and introduce the numbers game. So the numbers game is a dual game to the mutation game, numbers game. And it was introduced by numbers game. By Mozes, and also studied extensively by Eriksson. There's also a nice paper by Donnelly on this thing. Okay, so here is the numbers game in the context of an example so that I can not say so much. So let's stick with a very simple graph, this one here that we've seen before. Let's label its vertices 1, 2, 3, 4, let's say. So those are the vertices, maybe x1, x2, x3, maybe better. Those are the labels of the vertices. And let's consider a population on that graph. And I'm going to consider the same one that I did in my first lecture, -1, 2, 4, 3. That's a population on that graph. Okay. So let me remind you that we could play the mutation game. Okay. So I remind you that if we play the mutation game and say mutate at S2, then what happens is the following. So what happens to the population 2? The 2 turns into a -2, and then the sum of the directly neighboring vertices clone their populations and send them into the mutating position to cancel out the mutation. So if we mutate at 2, then the 2 becomes a -2, and then we have to add 3 plus 4 plus -1, so we have to add 6. So we get 4. Is that right? -2 plus 6 is 4. Okay. And the other ones do not change. Okay, now over here I'm going to draw another copy of the same graph, but it will have little open vertices so that we know which one we're talking about. So this is just another copy of the graph. And over here, I'm going to record the possible changes that could occur if you did the mutation game at the various vertices. So remember that the overall strategy of the mutation game is to increase populations. And at every stage, you have a choice of which city or node you want to mutate at. And maybe you want to increase the population by as much as you can, or maybe you just want to increase it by as minimal amount as you can. In any case, it would be useful to know how much the various mutations are affecting the population at the different points. So we just learned that if we mutate at 2, then the increase is 2. So I'm going to record this by putting a 2 here. Let's go through the other ones so we understand. So suppose I mutate here at this vertex here. The -1 goes to a +1, and then we add 2, and I get 3. So if I mutate here, I would end up going to 3. That would be an increase of 4. I will record that by 4 here. If I mutated here, the 4 would go to a -4, and then I would add 5. 4 plus 5, that's 1. And so the 4 would go to a 1, which would be a decrease of 3 or a change of -3. And if I mutated at 3, the 3 would become a -3 plus 6 is still +3, so there would be no change. So if I'm at this stage here and I'm playing the mutation game, then this secondary object tells me what the effects of the various mutations are. If I'm interested in increasing the population as much as possible, I would then choose this mutation. Okay. So now, so there's a kind of a map. I can go from here to here. Now let me do the same thing for this one. Let's see what the corresponding thing over here is for this second configuration that we've just obtained. What are the corresponding changes if we mutated now here? Okay, so we have to do some arithmetic. So if I mutate here, I get -1 goes to 1, add 4, that's 5. So it's a total of 6, yes? Correct me if I do my arithmetic wrong. So that would be an increase of 6. If I mutated here, I get -4 plus 6 would be 2. 2, so it would go from 4 to 2, so that'd be a change of -2. If I did here, I go 4 goes to -4 plus 7 is 3. That'd be a change of -1. And here, 3 minus 3 plus 8 would be plus 5. So it would be a change of +2. Okay, and now we ask, how can we just go from here to here without the mutation game? What are we actually doing? We're doing a new kind of operation purely at this level here, which we can call firing. We're going to call this firing. Firing at 2. At x2. What did that firing actually accomplish? Can you see? Well, what the firing does is the following. I'll try to write it down correctly this time. Okay, so if we have a population, say lambda, and I'm going to fire at x, and I'm talking about, so lambda is like a population on this graph I'm going to call a weight. That's an integer valued function on this kind of dual or twin graph. And if we have a weight lambda and we do Rx of y, what is that? So that's going to be minus lambda of y if y equals x. And it's going to be lambda of y plus a of xy lambda x if y does not equal x. Hope I said that right. So what happens? So if we fire at node 2, then what happens is that the population, or the weight at 2, changes to its negative. And concurrently, at the same time, the original weight here is replicated and sent to each of its adjacent neighbors. So this 2 gets sent to 4 at 6, the 2 gets sent to the -3 to give us -1, the 2 gets sent to 0 to give us 2. So if we sort of make a vector here, so let me sort of introduce a bit of linear algebra. So on this side here, let's say that the population P will be recorded with a vector, -1, 2, 4, 3. We have our vertices ordered so we can make a vector out of the population. And over here, this other population, which I'm calling a weight now, can also be ordered, and so we'll give it also some linear algebra kind of thing. So lambda, say, would be 4, 2, -3, 0. That's another vector. But now in round brackets. So I have these two different kinds of brackets distinguishing populations from weights. Okay. Then, what is the effect of this? This is correspondence here. Let's call this correspondence phi. How do we go from a population to a weight? What have we actually done? So lambda goes from populations. The populations are, say, P of x, to the weights. Let's call the weights lambda of x. These are populations, and these are weights. So this map, what is the map? Well, lambda equals phi of p. What is that? It's p times, basically, we're doing this. So what happens is that the population, okay, like what happens to 2? Happens to 2. We look to see what it goes to under the mutation map. And then we take the difference between this thing and the original. But this thing here was itself -2 plus 4 plus 3 plus -1. That's how we got the 4. So we want to take the difference between this and this. What it really amounts to is taking the sum of the neighbor populations and subtracting twice the original population. The difference between this thing and this. That's why there's a 2 here. And so that's just minus P times C, where C is the Cartan matrix representing the bilinear form. Cartan matrix. So from a linear algebra point of view, this is very nice. And basically what we are saying here is that we have a commuting diagram. So this diagram commutes. We have mutations this way, we have firings this way, and we have this identification of populations and weights. Of course, it's a true identification. We require a determinant of C not to be equal to 0 for there to be a bijection, a phi bijection. That means, i.e., that the graph X is not ADE tilde. So this correspondence doesn't quite work with the ADE tilde graphs because of the existence of the Perron-Frobenius vector, but otherwise it works perfectly and gives us a correspondence between populations and weights. So that means that we can now view everything, what we've been doing so far about the mutation game, we can view it in terms of this numbers game. So this is the numbers game over here. Okay, so let me give you an indication of why this numbers game might be interesting. Okay, so here is a theorem of Eriksson. Lovely theorem. So X is just a connected simple graph although actually one can jack this up to direct graphs, but we're not going to. So X is a connected simple graph, and we play the numbers game on an initial weight lambda. Suppose, but let's say, but only firing at strictly positive values. So the places where the dual weight is positive represents an increase at the mutation level. So if we're only interested in increasing, we should only fire at strictly positive nodes. So if we do that, then, so if we start, let's say lambda, if, maybe this is not exactly the theorem, but it's some kind of reformulation. If lambda is a non-zero positive weight, and X is, okay, then two things can happen. Then, if X is not ADE, or maybe I should exclude ADE tilde as well, then there will be, you will never, sequence will never terminate. The game never terminates. There will always be a positive node that you can fire at. And two, if X is ADE, then the game terminates always at the same weight. And the number of mutations, the number of firings, is independent of order. That means you have some ADE graph, and you have some, they're actually circle ones because we're thinking of this numbers game, and then you start performing various firings, etc. And eventually you get to some situation where you only have negative values. No matter what you start with, doesn't matter what you start with, as long as they're all positive. You start firing, eventually you get to something that's all negative. You can't fire anymore because you've agreed to only fire at positive things. And the final population that you get at is independent of the various choices that you make. You'll have lots of choices at various stages. So there's lots of different paths to go from here to here, but each one of them will end up in the same spot, and each of those paths will have the same number of edges, steps. So those of you know some Coxeter groups, this is somehow related to reduced decompositions of Coxeter groups, but this is just graph theoretical formulation. Okay, so now I want to turn our attention to some particle physics and apply this in pretty well the simplest possible case. The simplest possible case is A2. But it turns out that A2 is already very interesting and full of richness, suggesting that the entire story is actually incredibly rich. Okay, so let's look at A2 and physics. In particular, brief lightning review of the eightfold way, or Gell-Mann, eightfold way, and something called chromodynamics, which is sort of the strong force and things with quarks. Okay, so in A2 we only have these two nodes, and let's say we have two population of AB. Then the corresponding weights over here, we can calculate quite easily. So if we mutate here, we'd get minus A plus B, and so the difference will be B minus 2A, and corresponding difference here will be A minus 2B. So this is like the population P, which we'll record with a vector AB, and this is the weight, I guess lambda, which we'll record with B minus 2A, comma A minus 2B. And how to go from one to the other? Well, we can say that lambda is equal to AB, as a vector, times, here's our Cartan matrix multiplied by minus 1. That's how we go from one step to the other. Now, if we want to go backwards, if we want to find out what AB is in terms of lambda, well, we have to multiply by the inverse of this matrix, which is the following. Minus 2/3, minus 1/3, minus 1/3, and minus 2/3. So we get some fractions involved here. And the fractions correspond, so we get two sort of bases. We get sort of the root basis, consisting of what I at some point I call alpha 1, which would be the vector 1, 0, and alpha 2, which is the vector 0, 1. And now we have what I call the weight basis. Well, would be, let me call them maybe gamma. Gamma 1 will be minus 2/3, 1/3, minus 1/3. I'm going to put square brackets. And gamma 2 equals minus 1/3, minus 2/3. Okay, so what we have here is we have these two parallel games. You can play the game on the original graph, or you can play it on the weight graph. And we know how to go back and forth. The back and forth is given by the matrix, Cartan matrix, or it's negative and it's inverse. And so we then have a situation where we have two possible ways of looking at the same vectors. One essentially from this point of view, and the other one from this point of view, because this map phi that we have basically allows us to identify these two vector spaces. We can put everything on the same picture. And that's what we have over here. It's the same. I'm going to put everything on the same picture. Okay. So, but okay. So where are these vectors? Well, alpha 1 and alpha 2 are over here. So here's alpha 1. That's 1, 0, and here's alpha 2. That's 0, 1. And then over here, minus 2/3 and minus 1/3. So notice I sort of divide this up into threes. That makes it easier. So now this vector here, this is gamma 1. It's minus 2/3, minus 1/3. And this other one here is gamma 2. Okay, so we are now in the position of being able to describe what's happening here with respect to either of these two bases. And so we're talking about mutations or firings, and we can exhibit both of them on the same diagram. And so to illustrate that, without writing lots of formulas, I'm just going to show you what happens in a special case. So I'm going to pick a particular one, and we're going to look at what happens to a particular thing. We're going to do some mutating fire. So maybe to touch base with the physics one. So in the 1940s and 1950s, the physics community had these new particle accelerators and the bubble chambers and so on, and they created lots of new particles. So by the early 60s, there was this wealth of new particles that formed this kind of zoo, and they didn't know how to organize them. Okay. And there were new features, sort of new quantum numbers and such. And so it was a major problem of trying to organize these particles. They had names like delta particles and chi particles and mesons and neutrinos and various things. So that's sort of the physics angle. And it turns out that this diagram, remarkably, sheds a huge amount of light on what the physicists invoked. It's called flavor of symmetry. And then it turns out a few years later that it also, the same diagram also somehow encodes the chromodynamics of the color symmetry. So let me try to get at that a little bit by looking at an example. So what we're going to do is we're going to look at a particular element, this one right here, okay? Now that point in the ordinary coordinates, it's -1, -2. So this point is -1, -2 in the standard coordinates that you see. But in terms of these vectors, gamma 1 and gamma 2, it's also equal to, well, as you can see here, it's 0 times this one, and it's exactly 3 times lambda 2. So it's 0, 3. And you can interpret that to mean, well, if you take this population and you perform that phi operation, you take b minus 2 times this, you're going to get 0. And if you take this minus 2 times that, you're going to get 3. So this is just a phi map going from here to there. Okay. So there's these two ways of thinking about that point. So let's perform go through sort of the symmetric group, the Weil group, and how it acts on these two things. In other words, we're going to play mutations and firings sort of simultaneously. So the first one, now over here we're going to do mutations. So we could fire at, or we could mutate at vertex 1 or at vertex 2. If we mutate at vertex 1, we don't get anything. If we mutate here, we get positive 2 plus minus 1 is positive 1. And over here, we're going to do firings. And we're going to start with 0, 3. And we could either fire at 1 or fire at 2. So if we fire at 1, nothing's going to happen. If we fire at 2, to remind you what happens, is the thing negates. 3 becomes a minus 3, and a copy of 3 is sent to all the adjacent vertices. That's the fire. So that goes to 3 minus 3. Okay, so now we could do some more. We could do a 2 there. If we do a 2 there, we're going to get this one, minus 1, 1. If we do a 1 there, we're going to get, what happens if we get a minus 1? A 1. So minus 1 goes to 1, and then we add 1, so we get 2, 1. And that corresponds over here. We would get 3 minus 3, and over here, minus 3, 0. And then if we did it once more, we do the 2 here or a 1 here. In either direction, we're going to get. We take here 2, we get minus 1 plus 2. That's just what we already got, 2, 1. Let's do a 1 here, we go plus 1 plus 1, 2, 1. So that's what we end up with. And over here, we end up with minus 3. Okay, so now I can show you these things on the graph. So minus 1, 2, if we do the reflection, the first reflection in 1, and I should maybe tell you what the reflection in 1 is. So it really corresponds to the axes generated by these are really the reflection axes. So when we reflect in alpha 1 here, we're really reflecting with respect to this quadratic form. The quadratic form is this one here. That's the C matrix. And the quadratic form is 2x squared minus 2xy plus 2y squared. That's the quadratic form. So we're not talking about a Euclidean quadratic form. It's not a Euclidean reflection. So usually when you see etude diagrams in books and so on, the physicists, they like to draw them this way with the hexagonal lattice. But in order to actually get at that, you need to diagonalize the matrix and you need irrational numbers. We prefer not to do that. We want to prefer to stick with the quadratic form that the graph is actually giving us. Okay. Now that has the advantage that the reflections are all in the directions of the coordinate axes, so in some sense it's so easy. So if we go from minus 1, 2, let's say there, we go up to minus 1, 1, which is minus 1, 1. So there it is there, there's minus 1, 1. which also equals 3 minus 3. And then what else do we get? Then we eventually get 2, 1, which is over here. There's 2, 1. Anything else on the picture? No, those are the only 3 things that we really get. So we end up with this diagram like this. And actually there's another side like this. It's actually a third reflection having to do with this other positive group. And we get a diagram now which has, well, it's a very interesting diagram. This diagram corresponds to something that Murray Gell-Mann, back in the early 60s, got a Nobel Prize for part of what he did. He realized that this diagram is very much analogous to this family of elementary particles that were around at that time. So these are delta particles. They have some names. There was an existing family of particles that he could arrange in this fashion. And those particles exactly corresponded to the part of this triangular story that's contained in the root lattice. There's 2 lattices floating around here. There's the black lattice, which is the lattice generated by the root vectors. And then there's this finer or bigger lattice, the weight lattice, which consists of all of the points. But we're actually only interested in the intersection of what we can get from one of these things by adding root vectors. So in other words, only these ones. And so turns out that quantum numbers and various things that they had also sort of corresponded to the positions. And so he was able to say, aha, from the mathematics, there should be another particle down here. And that particle turned out to be what's called the omega minus particle. And that, he was able to tell the experimentalists where to look for it because he knew where it was in the story. And so then, beautifully, they found the particle a little while later, and everybody involved got Nobel Prizes. But more than this was also the start of the standard model, because then physicists realized that, wait a minute, there's something interesting about this diagram. And usually this diagram is presented in terms of threefold symmetry, in terms of sort of linear symmetry in terms of the representations of SU3. And that's a very rich part of the story, which is another thing to describe it. You can already see the sort of combinatorial structure of it here. So there were 2 other really important things that he was able to correspond with. He was also able to correspond with another octet. An octet consisting of, let me get this right. Well, actually, just exactly the roots. So these vectors here form an octet. This is called a decagon. Here there's an octet. And the octet involved the neutron, the proton, some other particle called sigma minus, another one called sigma plus, and then and there were 2 other ones here. And then there were also 2 more. I'm not sure exactly what they all are. But so this is the ordinary neutron and proton that we're familiar with. So that is also part of the story, and that corresponds to these things. So then in order to try to understand what was going on, they realized that there was actually something more fundamental, or seemingly something more fundamental, and that has to do with these other things, which let me try to introduce with the triangle. So this thing here, we look at these three, which are also another orbit under the Weyl group. Those three particles are called up, down, and strange. And those are the quarks, or some of the quarks. So the quarks ended up corresponding to these positions on the diagram. And this kind of, combinations that we get in here. So this particle here, for example, is sort of vectorly. It's like three up quarks. Just do a sort of naive vector addition. And this omega particle is like three strange quarks. And the neutron and the proton, the proton turns out to be up, up, down, and the neutron turns out to be down, down, up. This is all a dramatic simplification. It's a little bit more complicated than this, but okay. This is the rough idea. So that these three quarks ended up being like building blocks for the larger particles, and the way the larger particles are composed has a lot to do, it's really essentially contained all in the combinatorics of this diagram. The combinatorics of this diagram. And in particular, there's another another triple around, if I take the opposites of these ones, which are where? Red here. So I've got those ones. If I take this one, and this one, and I guess this one, then there's another triple of quarks. There is, in fact, another triple of quarks called top, bottom, and chart. Sort of levels of quarks. Okay, so this whole story is called flavor symmetry, and the idea is that these quarks are not actually observable in isolation, but they combine to give us these other elementary particles. They're observable. But then the physicists looked at this, and I realize I'm out of time, but I just have to say this because it's so interesting. So there's a whole other second part of this story that the physicists, after looking at this, they realize that, well, these things here are certain things called fermions, and they obey certain statistics. So actually, it's not possible to have three up quarks together. That contradicts the Pauli exclusion principle. So in order to make that work, they had to introduce another brand of symmetry. In fact, so then there's a repeat version. This entire story, roughly, is then replicated in what's called color symmetry, where we suppose that we don't just have quarks, but that quarks come in three different colors. Red, blue, and green. And then it turns out that the symmetry between these red, blues, and greens, which is sort of the media of the strong force, they're also naturally associated to these three simple weights. So in color story, this might be red, this might be red, that might be blue, and that might be green. And then the opposite ones are the antiparticles, red bar, green bar, blue bar. So okay, very roughly, the physicists have done all kinds of fabulous things, but sort of, although the mathematics is somewhat more sophisticated, it's actually in terms of fields and representations of SU3, the combinatorics is all, or mostly all, contained in this geometry associated with the A2 Dickin diagram, or the A2 graph.